Hello, everyone. Thank you for coming to the London Scala Users Group. Today, we've got two excellent talks lined up. We have Gabriele, who is going to speak to us about MUnit. He's the co-founder of Milano Scala, and he also organizes Scala Italy. He maintains MUnit, which is an excellent testing library. So I'm really happy to let him speak on it here.
Thank you. Can you see my slides yet? Probably not. Okay, no, I guess you can now. Okay. So hi everyone. As Zainab said, I'm Gabriele. I'm from London, where I actually am right now. So today I want to talk to you about MUnit, which is this testing library. So first of all, I would like to move on to the agenda for tonight. So at first, we're going to see some MUnit basics, what it is, when was it born, why does it exist, and which brings us to the second point, the reasons behind MUnit, the motivations for it to be even out there, and so some context about the library. Finally, we're going to see some design principles, which are, I think, that make MUnit interesting, at least to me. It's what makes me sort of passionate about this tiny little library. And finally, I cherry-picked one of the features that I like the most about MUnit, which is transforms. It was a hard choice, so at the very end, I'm also going to list some other of my favorite features, but we're not going to go deep into it for time reasons. There's a lot to unpack, but I picked transforms for a reason that will be apparent later, I hope so. So first of all, some basics, as I promised. It's a fairly young library. It recently turned 1 year old. It was 1 year old in February, I think, which feels like ages ago, considering all that happened the last year. But yeah, it's not that old. It was developed originally by Olafur Gerson, who's also currently a maintainer. Olafur at the time was working at Twitter. He was a software engineer at Twitter. He's now a software engineer at SourceGraph. You may know him for a lot of tooling, for a lot of tools for Scala, like Scala.ft, Scala.fix, and he's also the original author of Metals and a few other things. So this was no coincidence that he worked on this project, as we will see. And it was, again, born in the context of this Scala Meta project. And Scala Meta, if you don't know it, is essentially an organization, a GitHub organization, which serves as an umbrella organization for a lot of tooling projects and tool chains, such as the aforementioned Scala.ft, the Scala Meta itself, which is a data library for metaprogramming in Scala, and a few other interesting projects such as Metals and MUnit, of course. So a few other things. MUnit is virtually available for everything that exists regarding Scala and its platforms and versions. So the only not availability here are due to the fact that Scala native is not yet compatible with Scala 3, but other than that, we cover everything. And this is also thanks to the fact that MUnit does not have any Scala dependencies, which makes it easier. It's never easy to support this amount of combinations, but it makes it easier to move fast and to support recent versions of Scala. So, for instance, we recently added support for RC1 for Scala 3, which took surprisingly little work. So, again, it moves really fast. It's quite nimble in this regard, which is also why I know some ecosystems, like the type level ecosystem, was able to adopt it while migrating to Scala 3, because it needed to be up to date with the recent milestones and RCs. So I'm going to switch to the editor for some quick demo. So I hope the font is big enough. If not, please let me know in a comment on YouTube, and maybe Zainab can relay that to me. Otherwise, I'm going to start. So this is a very simple project. I just want to show you that I've set up a couple of basic things. Well, the Scala version, the name. Library dependencies, essentially I've added MUnit as a test library, as a test dependency, and then we have cats.effect, which will be useful for a demo later. You can ignore it for now. So then the only...
Gabriele, I think that we can, we would quite like it if you could increase the font size.
A little bit?
Yeah, let me check that. Maybe even a little more would be nice.
Okay.
Yeah, that's coming through pretty clearly for me. Cool. Okay. Thank you.
Cool. Thanks for letting me know. So, as I was saying, the only one thing that you need to add in order to use MUnit is inform SBT of the existence of MUnit as a test framework. SBT comes with support pre-bundled for some common test frameworks such as Scala tests, specs do, but it doesn't have direct support for MUnit, so you just need to add this line, which is in the documentation. So other than that, this is a completely blank project. So I'm going to create a Scala file here, which is our demo suite. So I'm going to show you how this works. So you create class, you extend MUnit function suite, and that's it. You can just start writing tests. So you have a test, for instance, that test that math still works. And then you can write assertions. So for instance, we can assert that 1 + 1 is equal to 2. So let's see whether this actually works. Running the tests here. I'm running tests in SBT because it's a little bit more convenient. You could technically run them here also in using metals in the editor. So you can see that the demo suite informs us that math still works. And it took us very little time to do so. So let's try to break this just to get a feeling of how it is. So we got quite a lot more. So we see we have some indication that the test went wrong. We have some other information, but essentially we obtain and we understand that 1 + 1 should be 2, but it's actually 3 in our tests. So I'm gonna stop here since we're gonna go dig into this output a little bit more in a second. So this is just a feeling of how a MUnit looks like. It's quite easy, I think, to get started. You just extend the suite, and then you just start writing tests. I hope you like how easy it is to start working with it. So let me just go back to my slides. So why does MUnit exist? I mean, we have plenty of cool libraries for Scala for writing tests. We have specs2, we have Scala tests, just to cite the famous ones. But also we have a lot of other libraries such as microtest and minitest. We have plenty of libraries. We have zeotest. So first of all, one piece of intuition that Olafur was tinkering with at the time, as I mentioned, he was working at Twitter, so this was kind of in the context of his work as far as I know. So it was like, can we try to reuse the JUnit infrastructure? Meaning, JUnit is quite an ubiquitous Java testing framework, which is integrated with virtually everything. So IDEs, CIs, test reports, and whatnot. But we don't use it in Scala unless you're writing compiler, I guess, because it's essentially kind of unwieldy to use from Scala. It has a very Java-like API. It doesn't blend well with the way we're used to writing Scala. So we tend not to use JUnit, which is fine, but the idea underneath MUnit was like, can we have a nice Scala API, but also have the power of JUnit and its existing integration underneath? So that was the first intuition. And then the second one was like, we realized working in different Scala meta projects, Scala FMT first, Scala Fix, Metals itself, that we were essentially using some test frameworks, such as microtest, or utest, but we weren't actually using the high-level API. We're just using the primitives and then building our own custom API on top of it. And this was because we needed some specific features for specific projects. For instance, Scala FMT cared a lot about diffs. So it has a lot of machinery to print nice diffs because when you're working on formatting, you care a lot about single spaces, visualizing exactly what went wrong in a diff from a string perspective. And Scala Fix, again, needed some extra infrastructure. Metals, we needed a lot of infrastructure since it's a language server, and it needs to essentially account for a lot of complexities due to the fact that it's running against different Scala versions. It may have flaky tests. It may have reproduction of bugs that are for which we have a reproduction but not a fix. So we'll see how this shaped the MUnit API, but essentially the idea is that MUnit came to life because we saw a pattern across all these little hacks that we built, little custom APIs that we built on top of different Scala meta projects. So Olafur essentially extracted them out, and then we validated them against metals at first. So I personally worked on backporting essentially MUnit on top of metals and see whether they could fly, and it did. So then it got polished, and that's MUnit as you know it today. So moving on to the design principles, which I think are interesting, meaning that I haven't seen them across a lot of other frameworks, or essentially you may see some ideas but not bundled together as they are here. So first design principle is that we tend to have one way of doing things. So we tend to have one specific and prescribed way of working with MUnit. When it's not possible, we recommend one, but we tend to have this embedded in the API, and we'll see what this means. And the second one is that there's a lot of attention to a lot of little tiny details related to the developer experience and to the user experience in general, that when you add them up, it makes for a very polished and refined product. If you take them singularly, it may not look at much, but I will show you a lot of things that you may give for granted when you start working with MUnit, which is great because they're essentially disappearing and making your life better without you realizing that. So about one way of doing things. So for instance, FunSuite is the only testing style. This is opposed to other libraries that choose to have a very customizable approach. For instance, in Scala test, FunSuite is one of the testing styles. So you also can have behavioral tests. You can have different DSLs for writing tests, and so on and so forth. And so you need to choose and pick your own style and build together a lot of traits to construct your perfect suite, let's say. So there's nothing wrong about that. There is simply, but the thing we wanted to explore in MUnit is essentially to have a single and unambiguous way of testing, which may be limiting, but also it's also liberating in a way, meaning that you can just start writing tests right away without reading documentation and without essentially having to choose first. Then you have this thing which is quite controversial, and quite a lot of things ask about this on the Gitter channels and issues. There is no matchers DSLs, and by matchers I mean stuff like asserting things with an English-like DSL, such as this thing should be a left or something like that. You're familiar with it, I'm sure. If you're using Scala, you come across a lot of DSLs. A lot less these days than it used to be, but it's quite common in Scala to write DSLs because essentially it's a lot easier than in other languages. So let me jump into a brief rant about DSLs. So these things are all valid ways of writing the same thing. So the either should be a right, the either should be a right, the either is right should be true, and so on and so forth. They're all valid, and it confuses me a lot. It doesn't just confuse me, it actually takes me out of focus, because sometimes I spend a lot of time when I use these kind of APIs, like wondering whether I've chosen the perfect verb, whether there is a smarter way of doing this, whether this is expressive enough. So I tend to prefer the latter form today, which is just assert one thing, like assert the either is right. It's a lot drier. I understand it doesn't have the same ring to it as the either should be a right. But if you take this out of the single line context and you take it on an entire code base, and I've seen this migrating stuff away from, for instance, Scala test to MUnit, a lot of the things you find when using DSLs are arbitrary. The differences in styles are arbitrary. Should be versus should be, it's a technicality most of the times, and a lot of times it's just niceties, which creates a lot of divergence and a lot of confusions, and essentially creates inconsistencies all across the code bases. Versus being limited in what you can do actually makes you go faster, in my experience. So to continue my brief rant, what I can find nice about DSLs is that they're nicer to read when you read a single line. That's really nice. Like for English, from an English sentence point of view, you have a very expressive sentence. But also, as I said, you have arbitrary choices at every corner. There is no obvious way of what is the correct way. And the focus shifts easily to, again, as I said, choosing the right verb. Maybe it's a problem that only I have, but I'm pretty sure it is quite common that you end up doing this by perfecting the perfect combination. Maybe there is a specific combinator for, I don't know, arrays that you didn't know about. You go look that up, and you lose focus on what you were testing. Finally, it's a minor point, but it's also harder to inspect. If you are like me and you like jumping into the code for understanding and debugging some behaviors, if you jump into the code of a DSL, you typically end up in some synthetic construct for just supporting the specific syntax, which doesn't mean much. Which meaning very practically, if you come and click on the should of the should be, you don't end up anywhere meaningful. Whereas if you do that on the assert, you see the actual logic that performs the assert, and maybe you can find an explanation for the behavior that you're observing. So it's a bit easier and accessible to inspect. So about the DX, the developer experience, I would like to go back to my slides and show you a little bit of a demo of a few things that are really nice and in MUnit. So let's go back to this example here. So you can see that there are quite a things going on here. So let's analyze them, because as I said, those are little tiny things that may look obvious, but they're not. They're carefully thought through. So for instance, you have an indicator here, which is stable and which you can grab in a CI log, for instance. So this is a tiny thing that makes your life easier when you don't have the luxury of having maybe syntax alighting or the ability to jump to the code, because maybe, again, you're reading a log in the CI. So you can jump to this indicator and you can go from one failing test to another. And you also have indicators for skip test and for success tests. Then it just prints the suite name and the and the test name. You can see the length of the test, the duration of the test, which is printed by default, which I think is the same default. Then you have the path, which is very useful if you're working like this from a terminal in an editor, because you can jump directly to the specific assertion. So you have the specific line which failed, which you can jump to, and then the cursor is here. Then you have this code frame, which highlights the line that failed. And this is actually done via a very small macro, which works across, again, Scala 2 and Scala 3. And this highlights exactly the line that failed. So if you have a few things here, and this fails, you see actually highlights line 5, which is the line that provided the failure. So this is useful for having context. Again, you can, of course, jump there, but again, if you're not in a non-interactive environment, this at least gives you some context about what went wrong. Then it tells you a few things, like values are not the same. It prints the value that you obtained, and then it prints a diff. So let me show you a few other cool things about this diff, which maybe may look obvious here, like this is a 2, this is a 3, okay? So interesting, but if you have stuff like class user, which has a name and some info, and then you have this class info, and then you have, I don't know, the age here. So suppose you have a few things like an expected value, which is a list of user. This one is me, and then you have info and one. And then you have partner, which is 32. So then you have this, and suppose you have now an actual result that you get from, and the actual result, you can test it against one another. So you have the actual, expected, and suppose that the expected one, so now this works, of course, and suppose that the expected one is something like this. So it's 30 instead of 32. So look at the diff now. So you have a diff which highlights the precise nested thing. So you have the field, which is age, which is the nested inside info, which is nicely formatted. And also notice that it prints out the name of the parameter, which isn't present here. And it also prints out here in the obtain the full thing, which you may decide to copy paste, for instance. So you can copy paste it here and fix the test. because maybe it's the text and it's fixing because the implementation is correct. So this is useful if you write these kind of expect tests or like snapshot tests in a way in which you have a specific value that you're expecting and you're just checking that the implementation returns that value. Sometimes you need to update the test itself. So this is a convenient way of doing so. So this is purposely copy-pastable so that you can do these kind of things. So again, there's specific treatments for lists and collections in general, and then you have these niceties on the parameters, for instance, of case classes. Now, another thing that I really like about the thing, so suppose that you have something like this. So now user and info are, user is enough. So suppose that now user is class, not a case class. So we can actually do something like this. So now we get a not so meaningful diff. So suppose that we do something like this. So we take the user and we override the toString to return just the name. So now what happens? What happens is that these two users, this one and this one here and this one here, are different, but you cannot print a meaningful diff because the name is the same. So you will not be able to print a diff. So what happens? So it says something smart. It says, look, the two values are not equal, but they have the same toString. So I'm not able to print a diff because if you print them, they look the same, but I'm telling you that they're different. So it actually helps you in doing that. Whereas what could have happened if there wasn't such care in the error message would be like, Irina is not equal to Irina, or something like that, right? So it takes the extra step of making sure that actually the two strings are actually different, that you can print a meaningful diff, and if it's not, it just prints a useful message here. So these are all examples of nice things that compose the developer experience when using MUnit. And I hope I demonstrated that there are a lot of tiny little things that are not obvious at first, but they play together really nice. So another thing that you may notice here, and we will notice later a little bit more, is that the stack traces are highlighted in my user code and dimmed for the library code. So this is actually another thing that was actually inspired by UTest, which has the same feature, and essentially helps you navigate through a long stack trace, which is not the case here, but we will see an example later where it becomes more useful. So back to the slide for 1 second. We've seen the developer experience using MUnit, and now I would like to point out my favorite feature of MUnit, which is a very elegant and powerful feature, which is transforms. So transforms in MUnit answers the question of how do you integrate with other libraries, other custom code that you have. And it also does it in a very Scala way, treating things as values, and then allow you to perform transformation on it. And I'm going to show you some examples right now. So suppose that you have, and now we can go back to the editor. Okay, so suppose that you have some suite. Okay, let's get rid of all this. So suppose now that you have some suite that returns a future. Okay, so you have a future, which is a Scala concurrent future. Oops. Sorry, fighting with Scala successful future, and then inside the future you have an assert equals of like 1 + 1 is equal to. So this works, which is unsurprising if you think about that. But if you write a wrong test, it correctly fails. So this isn't obvious at first because you are not you're doing this thing inside a future, right? So the future needs to execute before you can run these assertions. So this means that MUnit has out of the box support for asynchronous tests using future, meaning that when you return a future from the test, it will actually run this future for you and execute the future on, by the way, in a specific execution context provided by MUnit, and run the assertions. So suppose you are now writing future, but you're writing something like using something like IO from cats.effect. So cats.effect IO is, again, an asynchronous data structure, but it doesn't run right away, right? It just produces, it describes a computation that you then need to run. So if I do something like this, you would notice that this, if you look closely, it's unsurprising that these tests pass, because we would never run this IO. We would just return this IO to the test, and the test will like happily swallow it and do nothing. So the test works because we didn't run any assertion. So how can we deal with these kind of problems? Like maybe we have today's IO, maybe we have zero, maybe we have Monix task, maybe we have something else. Maybe we want to return a list from the tests or something like that. So transforms are the answer to this problem. So we have different kind of transforms. I'm going to start with the value transforms. So value transforms are transforms that work on the value returned by the test. So allows you to hook into the test before it's run, to take the value and to transform the value returned to a test. So let me demonstrate with an example. So we can do something like this. We concatenate the existing transforms, which include, by the way, the future transform that we saw before. And then we do new value transform. We give it a name. We give it a name, which is cats.io in this case. And then we can see that the value transform essentially takes a partial function from any to future any. So yes, we use any for flexibility here, but you can then refine the type. So the partial transform will match whatever we return to the test. So in this case, we're returning an IO of type IO whatever, and then we can just convert this IO to something that MUnit knows how to run, because it already has a pre-packaged transform that can run futures. So if you do unsafe to future, you're essentially running the IO as a future, and then this fails. And you will notice here that it fails. It preserves, again, the code frame in the correct position. And you can see the feature that I was mentioning before about highlighting structured stack traces in a more obvious way. So you can just take the demo suite lines and you see they're white, whereas all the cats effects internals are essentially dimmed out. So this is very few lines of code for writing a cats effect integration in a MUnit, which is, by the way, packaged in a library, but the library actually does the same thing. So you may even consider not importing a library as a dependencies and just copy pasting these lines, which I think is really nice considering how powerful this is and how simple it is to integrate with other libraries. By the way, the fact that you can execute futures makes this compatible with a lot of platforms such as Scala.js, which has a single thread because it runs on Node.js, and Scala native. So other approaches we make, which usually include like blocking the test, blocking the IO, so running these synchronously, usually fall short when integrating with things like Scala.js. So the generic approach of MUnit of working with futures underneath pays off in cases like this. So let me demonstrate just another kind of transforms. So you can have test transforms, for instance, which work, as you may guess, at a test level. So again, tests are also values. So you can take the test itself and write a test transform. So for instance, this is a transform that we have in methods, for instance, so which is adds the Scala version to the test. It does it only when running in the CI in case of metals. And the reason is that sometimes when you're reading logs, you may be running the same tests against different versions of Scala, and they may fail against some versions of Scala and not against some others. So it's nice to see the version of Scala against which the test has run. We can do that in essentially a one-liner. We can have a transformation here, in this case, from test to another test. So we can do test with name, which is a convenient constructor for a new test. And we can change name to just reuse the old name, which is the test name, and concatenate something like the Scala the version number string. So now what I've done, I transformed the test name. So instead of math works, I'm actually transforming this to print math works dash, and then the version of Scala it's running against it. So if I save this and I run this, and let's make it a success so it's easier to read, you can see the math works against 2.13.5, which is the version I'm working on right now. So finally, we have suite transformations, which I'm not going to write right now because it becomes boring after a while. But suite transformation work at the entire suite level. So you can do things like filtering tests or running some tests only against some versions of Scala or under some conditions or write. Or you can also do things like annotating tags. So you can define your own tags, which are generic metadata that you can associate to the test. And then based on the tag that you're associating with a test, you can use a suite transform to only do something when some tests are tagged with a specific tag. So for example, in MUnit itself, there are some tags that allow you to run specific tests only against specific milestones of Scala 3 because things were changing quite rapidly, and some tests worked against some versions of Scala 3 and some tests didn't. So we have a tag which is like only after N2, the milestone 2 of Scala 3, and then it works that way with a suite transform. So again, it's a super simple design. I think personally it's very easy to understand. You're transforming different things, the single values, the entire test or the suite, but it allows you to do a lot of powerful things, such as writing integration for different libraries, dynamically changing your tests as you go, depending on the environment, or again, deciding the behavior of an entire suite. So this is transform, and I hope it's apparent now why I cherry-picked this feature, because I think it's extremely elegant and powerful and orthogonal in the design of MUnit. That said, there are quite a lot of other features that I like. I'm going to go through them real quick. So MUnit has the concept of reusable fixtures, for instance, which means that your usual after all and before all and before any and after hooks that you have in suites usually can be bundled together in a value that you can apply to single tests. So you can have like this sort of a sandwich, a pre-made sandwich where you have some initialization, something that happened before and after a test, but you are not forced to add it to the entire suite. That you can just cherry pick what to use, which is really, really nice. Again, it's in the documentation with a few meaningful examples, and I encourage you to check it out. Also, MUnit helps you in dealing with flaky tests, which, again, as I mentioned before, was super important for metals. And flaky tests are essentially, well, the definition of a flaky test is a test that it's meaningful, it has to run, is successful in most cases, but sometimes it fails for reasons that are not easy to debug. So this is my definition of a flaky test. So it's still useful to run flaky tests because when it fails, it may provide some info, and it's good to know that you're running them, but failing the entire CI because flaky tests makes the entire CI unreliable. So what we do, for instance, in metals, is to take this approach, which is encouraged by MUnit, which is not failing the CI if a test is known to be flaky, and you can tag with the same mechanism of tags that I've shown you before, a test as flaky in MUnit. And then you can generate a report that you store. And again, MUnit gives you some facilities to store these tests currently only on Google Cloud, but it's trivial to write an integration for writing it in wherever you want. And then you can generate, like we do in Metals and MUnit, a table which gives you a summary of all the test runs that you've done, for instance, on the main branch. And you can then observe and decide whether a test is actually flaky or is just a bad test that you need to fix. So if you have positive success rate of 99%, it's probably a flaky test, which fails on 1% of the times. If it's like 70%, probably you wanted to take a look at that test and it's not flaky anymore. So again, the approach with flaky tests that MUnit encourages is to annotate the flaky test, mark them as such, observe through reports what happens to your test as you run them in a long period of time, and then decide, which is, I think, better than other approaches that I've tested in the past, which is we absolutely must fix all the tests, and that is not realistic sometimes, and it just makes you lose confidence on the CI, or just ignore them, which is pretty much as bad. Other nice things, which are smaller, you can mark tests as expected to fail. So it will fail the test if it succeeds, and so on and so forth. So you're essentially reversing the result of the test, which is a feature that was basically inspired by Ava, which is a testing framework for JavaScript. This is very useful if you have a reproduction to a bug in which you want to commit, but you don't have the fix. So you can just say, hey, I know this test is failing. I want to commit it and assert that it fails. So if you fix the bug, you will be forced to remove the test or to turn it into a successful test, because now it will fail because you fixed it. And this also helps if you fix it accidentally. You're like working on a fix which accidentally fixes some other bugs which you didn't think about. And those tests start to fail, and it's a nice feeling when that happens. It allows you to have great visibility. So then you have other nice features, which are assertion clues. So if you're using just a plain assert, you can annotate some parts of the expression that composes the final Boolean that you feed into the assert. So MUnit will print that out for you. Again, check the documentation. This is really cool, and it makes up for a lot of use cases people usually have for DSLs. And finally, a special mention for the Scala check integration, which is the only integration that MUnit ships as a module in the main repository. So this is part of the release process of MUnit. The reason why Scala check is so closely integrated with MUnit is that it's essentially paramount in the context of Scala libraries in general. So pretty much a lot of libraries depend on Scala check. So it would be quite bad if MUnit didn't timely ship its core functionalities together with the Scala check integration. So it's the only quote exception that we have. For all the other Scala integration, all the other MUnit integration live in separate repos because we want to keep the core very small and very maintainable. But Scala check makes a very good exception, I think. So that's it. That's all I have. This was a very quick introduction to the MUnit. I hope I made you at least interested and excited as I am about this tiny little library. Let me know in the questions if you have doubts, if you have positive experience about using it, if you have negative experiences, and any feedback is greatly appreciated. I don't have a lot of time to dedicate to these things, but I try my best to keep on doing my tiny little part in maintaining this great library. So thank you so much. And hey, Zainab.
Thank you so much, Gabriele. So we have we have a few questions. I have questions from me as well. I'll start with the questions from the audience. First of all, there was a question on the Bloop integration and whether or not it has it. And I think I already know this, but I wanted to.
Oh. Can you say that again? I missed it. What?
The integration with Bloop.
With Bloop. So it is integrated with Bloop, meaning that Bloop can recognize tests, which is why also Metals is able to display run the tests. Also has an integration, which another question that I sometimes get, has an integration with IntelliJ, which means that in IntelliJ you can also run the single tests and have the reports for the single tests in a unit. This was a recent addition a few weeks ago, months ago, I don't know, I don't remember exactly.
Cool. Well, thank you a lot. I think a lot of people have had a lot of positive experiences with MUnit, me included. It is definitely my favorite of all the testing libraries. We've been using it at the London Scala Users Group for the website for, I think since the beginning. And I think in its simplicity, it's really powerful. And I have to say, I agree with you about the rant on DSLs. Although I would say that there's, I don't know, in my head there's kind of a separation between DSLs as like a way of trying to use words and syntactic sugar, and then also a way of trying to express evaluation semantics of maybe your problem domain. which are like
I
two
understand.
different things.
Yeah, I completely agree. Yes, I was mostly talking about like trying to replicate English sentences, kind of DSLs, or yeah, that kind of. I agree. Those are different domains, and it may make the second one that you mentioned may make sense in some specific contexts. And yeah, you're essentially embedding a different domain language, which is yeah, a more interesting use case for the DSLs.
Yeah, the features that I really like. I think there are two that have struck out to me. You mentioned all of them, but it's actually the location, so that you can actually jump to wherever you decide when your test fails, and then also the clues are just excellent to work with.
Yeah, the clues are actually really important if you like moving away from DSLs. I tend to use a lot of assert equals kind of assertions where they're less useful, but if you're writing a lot of asserts on complex expressions, they are quite great. And yeah, for reasons of time, I didn't go through all of the features, but yeah, there are a lot of tiny gems that are really unique, I think. I haven't seen them in other libraries.
Yeah, and one thing I would say is that because of how simple it is, it means that you can tailor it to whatever your particular use case is. So as opposed to MUnit supporting whatever everybody thinks a testing framework should look like, it's almost like you can just build a tiny little bit on top of it, and then you get your perfect testing framework.
Yeah, I would never advertise this too much, but you can also write DSLs on top of it. Some people have done it, like yesterday, I think, on Gitter. I mean, it is really nice because, as you said, you can integrating thanks also to the transforms is really easy. So it allows you to develop an ecosystem essentially without having to bloat the core library, which is an explicit design choice.
Okay, yeah, I should make more use of those transforms, certainly.
They're really powerful. Like if you want some suggestions, like and ideas, you can take a look at Metal's code base, which abuses transforms for doing all sorts of things. But it's a good source of ideas.
All right. Well, thank you very much. I'll give you a little clap.
Thank you.
Right. We'll have a break now. Just a quick, maybe around 5 minutes or so, and we'll be back very shortly with Jacob. So thank you very much,
Everyone.
Hello, can you hear me?
Hello, we can hear you. At least I can
great.
hear you, so I assume everybody else can. All right. Well, thank you everybody for coming. I'd now like to introduce Jacob, who is excellent in the London Scala community. He's helped me out a ton of times at the user group, and he's also a great functional programmer. He's got a lot of really good ideas for how you can improve almost your day-to-day functional coding. And I'm really looking forward to hearing from him on how you can improve your testing with cats effect. So go ahead, Jacob.
Let's get started. Okay. All right. Yes. So before I start, I'd like to warn you that because I live near a hospital, well, in between a hospital and a police station, if there's a siren in the background, don't panic. It'll be fine. And what else did I need to say? Yep. Okay. Let's get started. So time warping with cats effect. That's what I want to talk about today. First of all, a bit about me. I am a software developer working at a company called Medidata. We make software for clinical trials. And sorry, I can't give you any vaccines, unfortunately. You can find me on GitHub and Twitter with this username. And as Zeynep said, I have a lot of ideas. I like types. I like functional programming. I have too many ideas. So if you want something interesting you want to work on and you need ideas, well, let me know because I have a ton of them. All right, let's get started. So it's Tuesday afternoon. You just finished your beautiful data pipeline, that you've written, most likely in FS2 if you're using cats effect. And you have all these cool error handling and these efficient windowed batching where you acknowledge messages, say in Kafka, in batches, right? You don't acknowledge every single one of them. You acknowledge every 5 seconds. And then when an error happens, you do your fancy exponential backoff and circuit breaker and all that jazzy thingies. Now, they all have a time component. So you're done. You've written the logic. But the question is, how do you test this? And that leads to the topic we want to talk about today. The problem we're trying to solve is that writing tests using a real clock is very, very difficult because you can't really use a real clock. But if you want to use thread.sleep, which is one way to do it, then you end up with a lot of flaky tests. As if you've tried it, you will know that when you put a thread to sleep, it's not guaranteed it's going to wake up immediately after the duration has passed. But then you can scratch your head a bit, think for a few minutes, and you probably still won't have an answer how you can actually test this logic. And that's what I want to show you today, how we can solve this problem. So in this talk, what we'll do is we'll go from the ground up. We will start with the lower level stuff, right? We'll explain a bit what threads are, why they're, and why we have these abstractions called thread pools and schedulers built on top of threads. And then using these abstractions and these ideas we've introduced, we will try to build a controlled scheduler on top of these abstractions. And then using this idea, we will look at one of the implementation of this idea, which is cats effects test context. And then we will look at how we can structure our tests so that we can have fast, efficient tests that are not flaky, running with logic that involves a lot of sleeping and delays. So in the beginning, we have Java thread, where you create a new thread, you pass it a runnable, and what happens is the JVM will have a thread, right? But then also creates a native thread in the operating system. And when you call run, it will run the executable. It will run the code that you pass it. And then when you call sleep, it will go back to the operating system and say, hey, put this thread to sleep. Operating system will say, all right, this thread should be shifted out of a CPU core right? So it shifts that thread out of the CPU core, loads another thread that's ready to run, and then runs it, continue execution. I didn't quite explain what runnable is, but a runnable is a simple interface with one single method that you implement, run. So it's a side effecting thing. Think of it as a side effecting function. Right? You implement it, and then you give it some code that needs to run. So here you can see that I create a new thread. I sleep for 1 second, and then I do a print line. I print hi. So when we actually execute it with t.run, what happens is it will initially sleep the thread. Again, it will go and tell the operating system that it wants to sleep this thread. And after 1 second, operating system will wake up, most likely wake up this thread, and it will continue execution. Now, what's wrong with threads? First of all, if you look at the previous slide, the code, it's a bit clunky to use, right? You have to explicitly create this new thread, and then you have to provide a runnable, and then you have to run it yourself as well. So it's a bit clunky. Not the most terrible API, but not the best either. More importantly, the threads have overhead in both processing time and memory. So what I mean by that is, if you have a look at stack traces, you will see all these. The reason why it's called stack traces is because the trace of all the stack, right? When functions execute, then the operating system keeps track of what functions are being called and who calls what, so that when an exception happens, then it can roll back. So every single thread has its own stack, which means when you create a new thread, the operating system have to allocate a certain amount of memory for this stack. So this is configurable in the JVM, right? And typically, the memory overhead for each thread is around 1 megabyte, maybe a bit less, maybe a bit more. Now, also we talked about sleeping a thread. So when we put a thread to sleep, the operating system will load another thread that's ready to execute onto the CPU core. Right, this is what we call context switching. So, we talked about a thread having its own stack. So the operating system the kernel or the operating system have to load all that memory from wherever it's stored in there. And there's also, because this goes into the operating system, into the kernel to perform this context switching, it has to perform a system call. This is how your user process, like the JVM, talks to the operating system to handle these shared resources. And this system call has overhead as well. Depends on what system call you're doing, but you're talking about maybe sometimes tens of hundreds of microseconds even. So if you do a lot of these context switching, it becomes more expensive. So what ends up happening is that in a typical JVM application, it's quite difficult to go beyond maybe a few hundred or 1,000 threads. Because the memory overhead, you can imagine, okay, 1 megabyte per thread. Now, if you have 1,000 of them, that's 1 gigabyte just in the overhead of a thread. We're not even talking about any other allocation, right? And so you can imagine, typically for a Java app or Scala app, we write backend services in them. If we're serving a lot of requests, and let's say we create 1 thread per request. Now, typically, what a backend service does is it takes the request, read contents, and then maybe perform some calculations, and then call another API or calls the database, and then it just sits there and wait for the response. Right? We have to wait for the response before we can continue execution. So in a typical a thread per request model, the thread is just sitting there sleeping, doing nothing until the request comes. The request and make comes back. And that means you can't really have thousands of requests that are waiting, right? You will run out of memory very quickly. And if you go back 10, 20 years with a thread per request model, like the Apache server, I think, you can see the scalability is really limited in that sense. I'm definitely not an expert in all these areas, especially the low-level things. So if you have anything you want to correct me on later on, feel free to. And also, I welcome questions anytime during the talk. So if you have questions, type it in the comments, and Zainab, you can feel free to interrupt me, because I think it's easier to explain at the moment instead of at the end of the talk. All right, so some smart people sit down and think about it really hard, and they came up with an idea. Right? How about, okay, we can't have too many threads, right? We don't want that. How about we create just a few threads and then make them run everything we want to run? And that's how the idea of thread pool comes into being. In the JVM, in Java, you have the executor service from the Java concurrent package. How this works is, instead of dealing with threads directly, now we only deal with runnables. So you have this executor service, which is kind of an abstraction. It says that give me a runnable, give me runnables, and I'll execute them sometime, most likely immediately. But if I have a lot of things to execute, then I'll execute it a bit later. So it's a simple interface. Definitely, I have simplified it quite a bit here for explanation purposes, but this is essentially what it is. And under the hood, what happens is that we have a few threads, only a few threads, right? And let's say we have 3 threads here. Internally, we have a queue of runnables. This is the little R thing that you're seeing there. And what each thread does is they just run an infinite loop, right? The logic is basically, check whether the queue has a runnable. If there is, take one, and then run that runnable. And then when I'm done, go back to the queue and to take the next one again. So they just keep running, right? Then they never get tired. And that's how a thread pool works. There are many different kinds of thread pools. Someone will create more threads dynamically to serve if there's a long queue, or there's a lot of different implementations. But the main idea is that a bunch of threads, a fixed amount of threads, takes runnables from a queue and run them. Now, when we're working in Scala, we have ExecutionContext, which is essentially the same interface. It's also simplified as well in Scala, so it's easier to work with and implement. But it's essentially the same idea. It's an abstraction over a thread pool. Cool. Now we can run runnables. The next problem we need to solve is thread.sleep. All right. We don't want to block a whole thread, because you can imagine if let's say thread 1 just completely goes to sleep for 5 seconds, that thread is gone, right? It can't continue doing anything. It's just completely blocked. So that's not good. We don't want to do that. So how do we avoid thread.sleep? So they sat down and then they came up with another interface which extends the ExecutorService interface. And instead of passing just a runnable and have it run pretty much immediately, they allow you to tell how long of a delay you want to have. So you have the schedule method you have to implement, give it a runnable, and tell them how long you want it to delay. I simplified the interface again just for explanation purposes. So in this case, it's just a simple number, and we're going to pretend it's nanoseconds. So you tell them how long you want to wait, and then what happens is, at the moment you call schedule, it will calculate how the current time, and then find using the delay you want. It will calculate when it should wake up, and then when the time has passed, it will run that runnable, and that's about it. So how this is typically implemented is that you have a single thread back in this whole thread pool, this whole scheduler, and what it does is it just continuously execute thread.sleep, right? So to give you an example, if I submit 3 runnables and the minimum delay between them is, let's say, 3 seconds, and what the thread will do is it will look at all the runnables that is scheduled and say, okay, the earliest time they are going to run any one of them is in 3 seconds. So I'm just going to go to sleep for 3 seconds, and then 3 seconds later, the operating system will wake up. The thread will look at its queue again and say, okay, now this runnable is ready to execute, and then execute that. That's essentially how a scheduled executor service normally works. If you're interested, you can look at the implementation in the Java concurrent package. And I think the one in cats effect, there's also one as well, so you can look at that. Okay, so we have these interfaces. We can run a runnable immediately, and we can submit a runnable to a thread pool where we can tell them the delay. Right? So the question is, can we use these interface to create something that doesn't actually run anything immediately, right? It doesn't run anything automatically until we tell it to. All it does is it just records the runnables and the time they should be run. Well, of course, the answer is yes, or else we won't be here. So we have a task that is inside there's a runnable, and we also have a timestamp where we want to run the runnable. So we created a little case class to contain this information. And then let's create a controlled scheduler. I'm not going to say the whole thing, it's a mouthful. So I'm going to call it a scheduler, a control scheduler, where we have a flaky clock, right, current time. And then we also have a record of all the tasks sorted by the run at time. So when you schedule a runnable, all it does is it's going to create a task, basically record when it should, calculate when it should run this task, and then just add it to the pool of tasks it needs to run, and then do nothing. So you can schedule hundreds and thousands of things to this scheduler. It's not going to do anything. It's just going to sit there. Okay, that's not very useful, right? We want to actually do some work. We want to actually run our tests and run our logic. So let's implement something to actually run. Right? Let's implement something that will artificially move time forward to by however long we want it to be, and then execute all tasks that should be executed during this time that we warped, that we jumped. Okay. So this interface, this method is called tick. You pass it how long you want it to move forward by. And what it will do, this is a simplified implementation, but the idea remains the same. We're going to move the clock forward, and then we're going to find one task, the next task that should be executed, right, by looking at the run at time if it's before the current clock that we just incremented, and it's going to run it. And then it's going to keep doing that until it runs out of task to do, right? Because if I have 3 tasks that should be run in between 0 and 3 seconds, it's going to execute all of them in order of the run at time, and then stop anything after that, because our clock is at 3 seconds. We're not going to execute them. They remain in the queue. Okay. Any questions at this point? I'll give you a few seconds to read it.
Cool. I think you've been coming through really clearly, actually. So everybody's been following.
Oh, that's great. Okay. I definitely would like to have some code highlighting and all that, but technology is not there yet. Okay, time to warp, right? So we have implemented this interface. Let's see it work. Let's create a scheduler. We're going to call it CTX, stand for context. And I'm going to schedule a runnable at 1,000 nanoseconds. And then when this runnable is run, I'm going to print warped. Okay. So remember the tick method we implemented. So now let's tick the time forward by 200 nanoseconds. Nothing happens because we have a task scheduled at 1,000. And then we tick forward again by 300. Nothing happens. And then we tick by 500. So now we're at time 1,000. And then our runnables run at this point. All right. So just a little bit of an explanation as well. So the runnable is run by the thread, right? The current thread that's executing all these ticks. basically is a single-threaded thing, right? It's being run by just the thread. So you need to make sure you don't have any thread.sleep or that sort of thing in your logic as well. Otherwise, it's not going to be good. So what you notice, you might notice from the previous few slides, is that it doesn't really matter, because we're using a fake clock. It doesn't really matter what time units we're using, right? We're using an arbitrary unit like 1,000, but it doesn't really matter what unit we're using. We can schedule as many runnables as you want, as far into the future as possible, because ultimately what happens is, what matters is the number of tasks that we have in the queue, right? And then we have the timestamp they should be run at right next to it. So, if I have 10 tasks that are all scheduled within 1 second, that should be run all within 1 second, and then I have another set of tests that stretch it out to be over, to be run in 1,000 years. It doesn't really matter, because when I move forward 1,000 years or I move forward by 1 second, it's going to execute them all the same, and the time it takes to execute them is all the same, assuming the runnables are doing the same thing. And this is how we achieve time warp. We just look at the task that needs to be run and when to run them, and then we just move the clock forward. It's pretty easy. Now, at this point, you might be wondering, it's like you came here, you heard about this cool cats effect thing, and the title even have cats effect in it, and then here I am talking about some Java interfaces, right? I don't think I've talked about anything that's Scala specific. You might feel a bit tricked, right? Because come on, nobody uses runnables really, right? We like to use our nice abstractions on top of it. So let me bring you towards the future. Okay, so I'll tell you a little secret. So all the effect libraries that you know and love, Zio, Monix, Cats Effect, Scala Futures, Java Futures, everything, all of them ultimately ends up being runnables, being run, being submitted and run in a thread pool. Let me give you a quick explanation with, let me break it down for you using the Scala feature. So we create our execution context. To recap, this is the same thing. It's a abstraction for thread pool, right? And we do some computation with our feature. That's the step one. And then in the next step, we do a print, right? We print the result of that computation. This is our feature. Now, what this actually turns into eventually is 2 runnables. We submit to the execution context the first runnable, where when it's executed, it will calculate some result, calculate some computation, 1 + 1. And then what it does is submit another runnable to the execution context, where when that runnable is run, it will print the result. Give you a second to look at the code. So, all your maps and flat maps, traverses, they all eventually turn into this thing. Okay? And it's all nicely hidden from you because writing this can be quite a pain, as you can see. What this means is that, what the concept where we talked about the controlled scheduler that we wrote before, the same idea can be implemented in all the futures and all the effect libraries that we know and love. And the cats effect test context is one of the implementation for to make it easy to work with in cats effect. You can find it in the cats effect laws library on Maven, and here's what it looks like. It looks very similar to the one that we wrote manually. With you create your test context. So in this case, it's pretty much the same as the controlled scheduler that we had before. Context shift is cats effect's way of representing thread pool, more or less. The timer is it's like a scheduler interface, the scheduled executor service interface we had before. And then let's run some logic. We're gonna print something, sleep for 100 days, and then print again. The same idea. We make sure, because we're dealing with I/O, it doesn't execute immediately on like a future. We're gonna make sure this I/O executes on the test context thread pool, right? The test context, and then we actually run the I/O. At this point, at step 2, nothing happens because our test context do the same thing. It just records what needs to be run and then sit there. So let's move time forward. We're gonna take it by 50 days. The print line for the first print line is being executed, right? Prints a high because there's no sleep, right? So the runnable was executed at time 0, which means it gets executed immediately. And then if we sleep for 100 days, so now the time is at 50, we move it forward by another 50, now time is at 100 days. The test context will say, all right, the second runnable should be run, and it is going to print, I have awakened, like we've written. So this is the manual way that you can use with use test context. It looks very similar to how we use our control scheduler before. So this is how I wrote tests for a while, and it works. It works perfectly fine as well. But it's a bit painful when sometimes my setup logic is in I/O itself, right? I might be using Doobie to change the database, and it's a bit dangerous sometimes if I accidentally submit run my setup code in test context. Well, test just hangs and it doesn't do anything. So I went to the Gitter chat, talked to some people, asked some questions, and they showed me another better way of doing it. And here I'm going to show you. So the idea is that we still have our app logic, like what we did in the last slide, and we also have another I/O, which is assertions. Right? So what that is, the idea is that you have the app logic that you're running, and you also have your assertions, which is kind of like an observer running. So they're all running in parallel, like all inside test context. So to explain it a bit, like basically you have 2 runnables, right? At least 2 runnables in the queue at any time. And this is a diagram, a time sequence diagram of what happens. Let's say we have some shared state in the middle. Let's say just a mutable variable. You have your app logic will perform maybe a modification and then sleep for some time and then modify it again. Meanwhile, in parallel, your assertions will do the same. It will assert that the state is at, let's say, 1 in time equals to 1, and then sleep for a while, and then assert again that now the app logic has run again, so that the value of the shared state should be at 2. And then finally, when the assertion is done, we're going to terminate the app logic using the fiber cancellation mechanism that cats.effect has. So this is quite handy because a lot of the time our time-sensitive logic is some sort of background process that's supposed to run forever and ever and ever. So if we don't cancel it, what's going to happen is we're just going to have a test that never finishes. It's just going to run forever, right? The test context is always going to see new runnables to run, and it's going to keep running them. So here's the implementation of the idea, where we create our context shift, timer, same mode stuff. I'm going to leave out the app logic here, but you can imagine, let's say the app logic is that every 5 seconds we will increment the state by 1. Okay, and then now we write our assertions, which is an I/O. We sleep for 5 seconds because remember our app logic will increment the state every 5 seconds. So our observer or our assertion is going to sleep for 5 seconds, wake up, check the state is 1, go back to sleep, and then check the state is 2 after 5 seconds. And then finally, it's going to finish. Okay. So this is the testing logic. You have 2 I/Os, remember. And then step 2 is kind of a bit of a test framework thingy. So it's something that you write once and you can reuse it across all your test suites that you want a controlled test for. So what we're going to do, how this works, is that we're going to fork our app logic, right? This with the start method. So what that's going to do is going to continue to execute this IO, and then the app logic will run in the background, even though it's not running, right? Because it's submitted to the test context. But from this IO's point of view, it forks it and it's running in the background. And then we're going to run our assertions. Now you'll notice that in the middle, I have this little sleep here for one nanosecond. So this is a little thing that it just makes writing assertions easier. So if I go back to the previous slide, you will see that our assertions always want to happen after the supposed modification from the app logic has happened. And in order for us to do that, we have to shift the whole assertions down by just a tiny amount, right? And that's what the little tiny sleep is doing there. And finally, when we're done with our assertions, when it's completed, we're going to cancel the app logic so we don't keep running it. So now we have our test, the test that kind of combines these two IOs together, and then we can execute our IO in the test context, turn into the future because that's something most test framework can deal with, and then we're going to take it forward for 1,000 days. So this is just a time to make sure that everything about the assertion is executed, and it doesn't matter what. This can be 1,000 years as well if you want to be safe. If you have logic that runs every year or whatever, probably not. But it's just because it doesn't really matter, right? Because as long as if we have no runnables anymore, then it's just going to skip forward to year 1,000 and we're done. So all these code. So the first half of the code is pretty much what you need to write. The second half is more of a setup code. I want to show you here because I want you guys to understand how this works under the hood. And that's it really. You can create your abstraction on top of it. You might want to create a new function that takes two IOs and then run and combine these IO together, like what I've shown you here. Or you might want to do other fancy stuff. You might want to have another IO that runs some setup before the app logic. You can do many things. And that's all there is to it, really. You can time warp now. Everyone's got the magic. Now, some final tips. With cats.effect.Timer and probably other implementations of the idea, when you have two runnables in a queue that are supposed to be run at the exact same time, what's going to happen is test context is going to choose one in random and run them. And this is intentional because it helps you catch race conditions. You might assume that if you execute one code after another with the same delay, it will run, but a lot of time it isn't. So it's good for that. And one also important thing to note is that because only your test context is controlled, right? You still have a lot of other thread pools like the Scala global execution context and maybe other thread pools that your application use. If you accidentally use them in your test, what you end up with is a test that hangs because your IO, your test IO never completes, right? It submits the runnable to another thread pool, and then the thread pool just runs it and immediately, and then it doesn't submit the runnable back. It just lost, and that's so if you have a test that's hanging or seems to complete but fail, then this is something you can look into. So some examples, if using Doobie, then you pass it a bunch of thread pools, right? The blocker thread pool, the normal execution thread pool. You need to make sure they're all test context, right? Similarly for futures, if you're running futures manually, you need to make sure the execution context that you're using, or when you call it map, the execution context you pass into map, are all controlled test contexts. Otherwise, they get lost. Similarly, if you're using external libraries, sometimes they like to run their own thread pool. Hopefully, you should be able to override that and then pass in your test context to it. Now, if you have a library that you can't override, for example, I think AWS V2, the SDK, I don't think you can override it, not fully anyway, then you can't really use it in your timing-based test. So the best thing you can do is to create an abstraction on top of that, and then use that to run your test, which you probably should do anyway. You probably don't want to use the AWS V2 interface directly because it makes it harder to refactor. And finally, I just want to reiterate that all these mechanisms, right, the first half of the talk, they're all built on simple primitives and interfaces that are common to all JVM ecosystems. So you can do this in Scala with all the different APX systems and features. You can do it in Java if you want to. And this idea is also transferable to other languages. If you have a language that have abstraction for a scheduler, right, for a thread pool, then you can implement the exact same idea as well. Okay, finally, I want to acknowledge a few people on the cats effect chat. They helped me understand the nicer way to run these tests, and they're also most of them are also heavy contributors to cats effect, so they wrote the test context class. So yeah, special thanks to them, and that's all I have today. Any questions?
Thank you very much, Jacob. Let's wait a bit for questions. I also wanted to just out of my own curiosity. So let's say you use cats effect, and while I haven't used test context, there are lots of other tools which I guess just the overall plumbing is just really good for testing anything which is asynchronous, particularly things like, even using the timer. If you use a timer throughout the code, then you can, put your own current time in, which is really useful. Then some I hesitate to say archaic code bases, but some people would, just default to system.currentTime when you want to get something. And so I found timer to be very useful.
Yes, that's a very good point. I didn't mention that in the talk. But yeah, remember in our controlled scheduler, we have our internal clock, right? And yeah, that's why the test context has a timer exposed, so you can use it, and you can have controlled, completely deterministic tests that way.
Yeah. So if you have your app logic, the timer that it's using is the same one that the test context is using. So you can, get the current time that way. So a question is, if the runnable throws any exceptions or crashes, does the tick still work?
It will fail just like, it will fail, or everything will fail, unless you have a catch, right? Unless you have a catch, or in the cats effect terminology, you have some sort of what's that thing called? Recover, right? If you recover, then it'll still work fine. But if you don't catch it, then it's just as if you get a stack trace, and then everything fails out. But your test will still fail, so that's good.
Looking at the code, it might do some special reporting as well. So I'll share a link to the actual test context class is there if anyone's interested in looking at it. So another thing on test context is that it's very much it's not highly popularized, I suppose. Like it's not many people talk about it, so it almost feels sometimes like it's internal to like the cats effect laws, as opposed to something that people expect you to use as part of the API. But what were your experiences with that? Like, do you think that it's a stable API to use?
I accidentally discovered it. I was like, oh, this is not private. I'm going to use it, and I used it. I was like, oh yeah, this works great. So, and I think it's kind of public. I wouldn't say it's not very well popularized, and I think it's a great idea in general. Not just for cats effect, but you have the similar stuff in Zio as well. I think it's called test clock over there. I think it's a great way to test things because we have at work I have quite a bit of a lot of background services, background jobs, and a lot of timing components involved. And this allows us to run tests deterministically, and they're not flaky, which is and then they're fast to run as well, which has been amazing for me. So I personally have good experience with it, and I looked around. There was no talk popularizing that, and I feel like someone has to do something about it.
Yeah. This is the start, right?
Yes.
It's because they're all Daniel and Fabio and everybody. They're all so busy popularizing the other really cool parts about Cats Effect that they forget about testing. Testing's really cool.
Yeah, they certainly built some cool stuff. Yeah, the Cats Effect 3 is really cool, and if you remember the context shift that we saw before, that's going to be gone, I think, in Cats Effect 3. Which means you'll be using ExecutionContext directly, which makes it a lot easier when you're integrating with existing applications that might use features.
How have you found the Cats Effect 3 upgrade?
Haven't done anything about it. No, yeah, haven't really looked at it. But I think I've looked at the interfaces, and I think it makes a lot of sense. I'm really excited. There's a blog post on how the new scheduler works. So I highly recommend reading that. It's very, very informative. I learn something new every time I read what Daniel wrote. So it's quite exciting because I think they claim that it's the fastest thread pool implementation on JVM. They have obviously done their tests, so I believe them. And looking at what they've done, I think that's pretty cool. So definitely recommend reading that blog post. I think it's on type level. We can maybe post a link to it.
Yeah, I think I've already done so. Is it the Wi-Fi as a fast one? So
yes, I think so. Yeah, that's right.
Yeah. I've posted it once. Let's post it again so people know. Yeah, that's awesome. That I really like that post actually. It goes through the history of I guess different implementations of effect handling. So I didn't realize that that Cats Effect 3 is inspired largely by Rust's Tokyo.
Yeah, I didn't know that
either. Which is really cool because Rust does a lot of it is really cool. It does like it's been in the Rust space, people have been exploring different futures implementations for quite a while. So it's nice to see that cross-pollination.
Definitely, yeah. There's a lot of things to learn from the Rust ecosystem, I think.
Yeah. So I still need to read, to be honest. That post it's really it goes into a lot of detail on why the Cats Effect handling is good. You've mentioned a few things here already about why you shouldn't use threads so much. Potentially why fibers are better than threads as well. So this is actually, yes, I would say this talk is quite a good primer to that post.
Definitely, yeah. I think it gives you a bit of. I reuse a lot of the concepts. Right, the introduction is similar. So, but then later on to go into the actual implementation of the new scheduler they have, and I won't spoil it. It's very exciting, and you look at it, it's like, wow, these guys are very, very smart. And, why didn't I think of that, right? But now you look at it, it's like, yeah, now I understand it, and maybe in the future you might be the person implementing it. So, yeah, it's good to know about these things.
Oh, well, so one last question. Do you have any online material? I've shared the link to your talk, but are there any repositories where you can see like small samples of using test context for various scenarios? Or do you have any?
don't have anything at the moment. Maybe I should whip something up. I'm not sure whether this is something worth contributing to existing test frameworks, because as I said, right, with my slides before, where you have this common setup, it's a very basic use case, right? Anything from step 2 is pretty much common. Sometimes you might want to do more things, right? You might want to take another IO for setup, for example. So I'm a bit unsure whether this is something that's can be contributed to, like with existing Scala tests. Just like Scala check integration, it can be integration with existing applications, and they will implicitly provide you with a controlled test context which you can use in your test. Yeah, I have to think about it. Maybe I'll contribute it to MUnit, right, or Scala test.
There's actually there is a cats.effect test library that Daniel wrote, though I don't think that covers test context. But I'll post that here as well.
Yeah. At least with the projects I'm working on, we kind of write our own test framework to wrap around this logic.
But it's so minimal, so it makes sense to do.
Yeah, okay. I think having an example app will be quite helpful.
Cool. So I think that's everybody's questions. Let's see how we're doing for time. Well, why don't we, since on the agenda, we're going to catch up and discuss in Spatial Chat. So why don't we head over to Spatial Chat just for a little bit, and I'll share the link. If anyone wants to join, it's a nice place to just have casual conversations.
Yep, I'll talk to everyone there. Thanks for coming. Had a great fun. See ya.
Thank you very much, Jacob.